Okay, so we have basically finished up the first section of the course as I outlined it at the beginning. Right? I said the first thing we're going to do. That we were going to do was look at functions from R into R3, and then the second into Rn. Say the second to look at functions from Rn into R, and the third to look at functions from Rn into Rn or M. Really, to be honest, we're not going to do it in different spaces. It'll be the same vector space. Just to give you more of a sense of the structure, in each section, we'll start out very simple, and then at the end of it, accelerate to some sort of high level of complexity, and then it'll drop down again as we enter the next section. Okay, so what we had last lecture was sort of like the local max, and now we're starting down. We're dropping down to a low level of complexity. And then at the very end, it's just going to, the complexity will just increase until the very last day, and then that'll be the end of the course. Just to warn you. Okay. I think the second section is probably the easiest of the sections. So if you've made it past curvature and arc length parameterization and stuff, this should be the second section. Even at its most complex, it should not be any challenge. Okay, so 15.1 functions of several variables. Functions of several variables. Right? So so our functions are going to have our functions are going to, who are we missing? Are we missing? Yes. No, sorry.
And the fire.
There was a fire. Oh, very good.
And so they had to run outside for 45 minutes.
Oh, really?
Until just then.
Why didn't we get to go outside for 45 minutes?
A lot of people were in the showers, so it's kind of
Oh, I see.
It was at like 9:15 until 9:55.
Oh my gosh. Okay. Well, yeah, I didn't know. I know. I apologize on behalf of Scripps.
It was someone in class.
It was what?
Someone vacuuming, and the vacuum got stuck in the rug, I guess,
and caught on
fire. Yeah.
I see. Yeah, I know. Yeah, that's yeah. Okay. So right. So it's a real valued function, right? And it has several variables as the input, right? So now, Melissa, we're switching sections. We're now entering the second section. It'll be sort of easy for now, for the time being. Functions that take in a bunch of variables and then spit out one number. Okay. So the main question is going to be, how do you define the derivative? Right? How do you define the derivative of such a thing? Right? How do you define the derivative of such a thing? It's going to be a little bit tricky. Okay. Okay. So right. So functions of several variables. Right. Blah blah blah. Right. It takes in a vector and then spits out a value. Okay. Previously, you remember that our outputs had the vector symbol on top of them. Right. Previously, we were looking at guys like this, where the output was a vector and the input was a scalar. Now it's the opposite. The input is a vector. The output is a scalar. That's why there's no vector mark. No vector mark on the F. Okay. Just notation. Okay. Okay. So here's a sort of like standard example of such a function, the norm function. Right? So f of x is the norm of x. Right? Because it takes in a vector and spits out a number, right? Namely the size of the vector. So we can look at this from several points of view. just algebraically, right, let's say, well, the norm of x is defined as x1 squared plus x2 squared plus xn squared to the 1/2. Right? You can you can look at it. One could think of this from the point of view of maps. Right? So you have Rn here, right? And it's a map. It's a map onto the real line, but starting at 0, only the non-negative part of the real line. Right? Right. So at every at every point in space, right, it's going to associate some height. Right? It's going to associate some number. That number is, of course, the distance to the origin, the distance of the point to the origin. So that's one way of visualizing it. Another way of visualizing it is to think. You could say like I associate to each point here some color, right? And maybe the hotter colors. This is usually how one does it. The colder colors represent lower numbers. The hotter colors, like red, represent the higher numbers, right? So this you'd see in that case, right? You'd have something like this, right? You have, maybe I'll just do it in R2 because it's easier to draw, right? Right. The coldest numbers, the coldest colors would be here, and as you went away from the origin, the numbers would get hotter and hotter. The colors would get hotter and hotter. Okay. So you can think of it as a map or a coloring. Another way you can describe such functions with graphs, right? Can describe with graphs, right? You say if you have some function, right? So you have some function from R2 into R, say. Then the graph is all things x, y, z in R3, where z is f of x, y. Right. Right. That is, one thinks of R2 lying inside of R3, right? And then to each point, right? You take only the points where the z coordinate equals f of the xy coordinates. Right? So, for example, if we're looking at the graph of the norm, what does that look like? Right? If we look at f of x, y being the norm of x, y, what does the graph look like? Don't blurt it out, but just think for 20 seconds and then tell me. Okay, take 10 seconds and draw the graph of the norm. Okay, what does it look like? Lily, what does it look like?
Would it look like an absolute value?
So, yeah, kind of. What do you mean, like an absolute value?
Like the V.
So I have the V here. That's so far so good. More, right? So it's in three dimensions, right? So So certainly, if we were like in looking at f of x equals the absolute value of x, right, then it will look like this, right? It will look something like this. Now we're looking at a function on R2, right? So at every point xy, you're going to associate some height that's going to be the norm of xy, right? And then you go up to that height, right? So
I don't know.
that's okay. That's okay. Right. So think like this, right? If you have the origin, well then the height is going to be 0, of course, right? Does anyone want to say? Paul?
Will it always be positive because it's in like the magnitude?
Sure. Sure. It'll always be positive. Right? Yeah. So yeah. So it's actually not so easy to think about it. So right here are the inputs. Right. The inputs are R2. Right. And that at each point in R2, you're going to associate a height, namely the norm of the vector xy. Right. So if this is my xy here, right, then I'm going to go from there up to a height z, where the height z, right, this height z is going to be the norm of xy. Right. The height z, being the norm of xy, is the distance of that guy to the origin. Right. The distance of that thing to the origin. Right. So at each point, you're going to have a point floating above it at this thing's distance to the origin. So yeah, it will look like an absolute value, right? Because if you doubled that guy, well then you're doubling the distance to the origin, right? So at this point here, well, the norm is going to be twice that thing, right? Right. Let me ask you this: suppose I look at points here in a circle, in say the unit circle. On the plane R2 here, right? What are going to be the heights there? They're all going to be 1, right? So all these guys are going to be at the same height, right? Okay, if I go distance 2, well, it's going to be 2, right? Okay, all these guys are going to have points floating over them at a height 2, right? And so on and so forth, right? You see that. Right, the points, right? If I cut the graph at height h, well, I'm gonna see that those points all correspond to points whose distance from the origin is h. Right. So what do you see? It is the graph of the absolute value function, but spun around to make a cone. This is a graph. And in general, graphing is kind of a pain. Okay, so there's one trick that's commonly played to visualize this sort of function. And it's one that we're basically foreshadowing or using already. It's the notion of level sets. You say, where does the function attain the value h? Okay. So you fix some h, and you say, where does the function attain this value? So, for example, if f of x is, again, the norm of xy, right? You draw the function as a map. You draw the function as a map, right? It's a map from R2 into R. It's a map from R2 into R. And you say, okay, let's fix some h, right? Let's fix the height of 1. where does the function attain the value 1? And maybe we already answered this. So where on what points x, y does f equal 1? Peter?
Unit circle.
On the unit circle, right? Okay. Right. On this circle, this is the level set. One denotes this by L1. The level set of height 1. Right? If you're looking at L2, well, that's going to just be the circle radius 2. Right? This is L2. Right? This is L3. Right? And in general, LH is going to be the circle radius h. Right? For this function. Let me write up. Let me formalize this. So here's the definition. You have some function from Rn into R. LH, which is all vectors such that f of x equals h, is called the level surface at height h of f. The level surface at height h. It's also called f inverse h, the preimage of h. Yeah, Melissa.
When you said LH is the circle of radius h, is that just for this example?
For this one example, yeah. For this
so
one
how do you
example.
know what shape it would be?
In general,
Yeah.
like for a general function, you have to think about it.
Okay.
Yeah, it's not obvious. You have to figure it out. Basically. I think we'll do some examples. Yeah, we'll do some examples. Okay. Okay. So just introducing the terminology here, right? I kind of like this notation better than L sub h, which who knows what that means. F inverse h to me looks like you take your height h, right, and then you pull it backwards through f, and you see what things got sent to h, right? See, look at the things that got sent to h, right? And that's the level set. That's the preimage. Okay. Everything that gets sent to h is the level surface or the preimage. Right. Once you have your collection of level sets, then you can visualize the function easily, right? So once you know what the level sets look like, you say, okay, well then if I wanted to graph this guy, I see that at around here it's going to have a height of 1. Here it's going to have a height of 2. Right? On the circle of radius 3, it's going to have a height of 3, etc., etc. And that gives you the graph and the function. Right? So knowing the level sets explicitly gives you the graph and the function. Okay. And that actually gives you sort of a different way of thinking about the level set. So in that case, you see that from that point of view, you see that the level set is actually the projection on the domain of the intersection of the graph of f with the plane z equals h. That is, just as you can go from the level sets to the graph, you can go from the graph back to the level sets, right? What's the level set at height h? Well, you take the plane at height h, you chop it through your graph, and you project that thing down onto the domain. That thing is the level set, right? Obviously. Right? So you chop through your graph at height h, and then you project that intersection down onto the domain, and that gives you the level set. Okay. Okay. So let's do some exercises. First, so the exercise is to find level sets and use them to graph the function. Okay. So here it is. F of x, y is x squared plus y squared. Okay, so take a minute or two and find level sets of this function, and then use them to graph it. Okay, so what do you all get? So let's think. Right. So here's R2, here's R. Right. The outputs are all going to be positive. Right. So what do you get? Sarah, how about you?
I think we're all confused.
You're all confused. Oh, thank you. Okay, so what's the confusion? What's a level?
I don't think we know how to start.
How do you know?
Well,
Okay, so just think, right? What is a level set? It's all the points that get set to a particular height, right? So if I say what's the level set at height 1, I'm asking what guys have a value of 1, right? What x, y are such that x squared plus y squared equals 1?
Well, you get 1, 0, and then 0, 1.
1, 0, 0, 1. Any others?
And then negative.
Negatives, yeah, right.
negatives.
Any others? Right. what if I ask? Here's a height 1. What guys get sent to? What guys are such that x squared plus y squared equals 1? Well, certainly these guys, right? Yeah, but there's more, right? Infinitely many more. It's the whole circle, right? The unit circle. Right? This whole thing gets sent to 1. Right? So this is the level. This is the level set at height 1 for this function. Okay. What about the guys that get sent to 2? Who gets sent to 2? Sydney?
Circle radius 2.
The circle radius square root of 2, right? So here, maybe it's better if I say this, if we go to 4, say. Who gets sent to 4?
Circle radius 2.
Circle radius 2, right? Who gets sent to 9, right? So this thing is L1, this thing is L2, right? The circle radius 3 is what? I'm sorry, this is L4, excuse me. The circle radius 3 is going to be L9, right? The circle radius 4 is going to be L16, and so on and so forth, right? 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 LH is going to be the circle, right? It's all xy in R2, such that x squared plus y squared equals h, right? In other words, it's the circle of radius root h, right? And so these are the level sets for this function. Okay, and you notice that they will help you graph the function, right? You say, well, look, around over the circle of radius. So now this is my domain. I've taken this thing and I'm lying it flat now. Okay. You say, okay, above the circle of radius 1, I'm going to have points floating around at height 1. Right? Above the circle of radius 2, I'm going to have guys floating at height 4. Right? Above the circle of radius 3, I'm going to have guys floating at height 9. Right? Above the circle radius 4, I'm going to have guys floating at height 16. Right? And so on and so forth. Right? And so you see the graph of this thing is parabolic, right? It's a parabola spun around. It's the rotation of a parabola. Yeah, Elena.
Are they always circles?
No, I'm just doing that for you. Yeah, it'll depend on the function. We'll do one that's not in a second. Just for simplicity, for ease. We're starting off with the guys that are circles. Melissa.
I'm a little confused. Like, if it's in R2, then how come the graph you get in the end is in 3 dimensions?
Right, you have a function from R to R, right? It's the input is real, right? The input is 1-dimensional, but the graph is in R2.
Oh, okay.
Same thing here, right? We have a graph that is on R2 going into R, right? And so the input is 2-dimensional, but the graph is 3-dimensional. Right? The graph is basically going to lie in this times this, R2 cross. Really, this R3 you think of as R2 multiplied by R, right? Just like here, we've got R and R, and the graph lies in the product R times R. Right? That's why, if you have something like R3 into R, you can't graph it, because you'd have to have a 4-dimensional screen. Is it becoming clearer?
Yeah.
Okay, good. Okay. Do I hear wailing?
I'm trying to think about R3 into R.
Oh yeah, okay, good. That's something to wail over. Yeah, you can't. There are tricks to do it, but basically. There are some people, or at least there used to be some people, who were said to be able to visualize 4-dimensional objects. My thesis advisor in college was a man named Thurston, William Thurston. And all of his work was in four-dimensional space. Like his entire body of work, and it was tremendous, was in four-dimensional space. And so he was one of these people who was said to be able to see things in 4 dimensions. And you know, I sort of joke that, but it was true that it was very hard to getting any information or knowledge out of him as a thesis advisor, because I'd come in and I'd say, well, Professor Thyssen, here's what I'm thinking, blah, 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 blah. And then he would, you know, make some scratches on the board, and he'd say, yes, yes. He'd make some scratches, and then he'd say, it goes like this. I say, you see it, don't you? Yeah. But he was, I'm afraid he's passed away, but he was like a genius among geniuses, I'd say. He was one of the winners of the Fields Medal. That's the analog of the Nobel Prize in mathematics. If you'll allow me a story, the story is that, and this is, I don't know if this is true or not, but the story is that when Thurston was an undergraduate, you know, he was sort of like a poor student and would come into class late, you know, not pay attention, you know, sort of like not really a good student. But one day he came in, and there were all these problems on the board. It's like homework problems. And he sort of writes them down, and then he, you know, the week after, he comes back in. He says, "Professor, those were really hard problems. You know, I was only able to do 3 of them." And the professor says, "Those were unsolved problems." That wasn't homework. Those are unsolved problems. And then so. Yeah, so that's a story. I don't know if it's true, but anyway, he was a nice guy, even if incomprehensible. Yeah. Yeah. Okay. Yeah. So. It was kind of interesting in those days because you know so I was at Princeton, and the emphasis is not on teaching, it's on research, right? So you don't expect actually to have a good teacher, right? It's not necessary. That's not why they're there. They're there because they're, you know, the greatest researchers on the planet. But interestingly enough, and this is something that you guys probably won't get, I hope. One actually learns quite a lot from bad teachers, because you have to, then all the burden's on you to structure the knowledge and everything. So it's actually quite instructive to have a bad teacher. Maybe I'll spend the rest of the semester teaching poorly, just off the top of my head, just so that you guys can have the experience. Yeah. No, but I really learned a lot from teachers who were completely disorganized. Okay. Okay. So, sorry. No? Okay. So here's another one. F of x y equals e to the x minus 1. Okay. E to the x minus 1. Okay. So again, I'd like you to figure out what the level sets look like. So take 2 minutes and see if you can do it. Okay, turn to somebody next to you and say what you have drawn.
I mean,
I agree with this, it's very strange.
X
Yeah.
becomes square, X is greater and Y.
So, no, when e to the 0 is 1.
X is
So
bigger
this is
than Y in
L1,
comparison.
because
You start off with
Wait, is it?
here,
Oh,
and
it's
then
e
you-
to the x.
It's just double here.
Yeah, it's
Like,
it's just a circle. Yeah.
It's not like it's
But then,
Yeah,
that's
but
because,
like, that's all I got.
if you want to go towards 0, Y becomes really big and then X becomes really small.
That's a
So
very
then,
different
like, the one
question.
right behind 0 is right there.
Yeah.
As you want to approach like infinity, X becomes really large and Y becomes nothing.
I agree with that.
But I don't know.
You guys here. So it just
I'm
starts
not
off
sure
like a
what it
cubic.
is. Do I? Yes, I do.
Yeah.
Yes, that makes sense. Yeah, I'm not sure if that's for L1. Well, I mean, L2 is
squared.
have 2 common 0. Then 0 common 8.
Okay, would
You keep
anybody
on
like
going if you wanna make
to?
it
Would anyone like to make a guess?
negative, like-
Would anyone like to say what they got? L of h, right? L of h is going to be all points such that the function is h, right?
It's also linear.
All guys, right? So here's our domain, and then right, there's our outputs there. And you see that we're not going to get anything that's negative, right? Because you have e to the something. E to the something is not going to be negative. So it's above, everything is above the axis. Okay, anyone have any guesses? Alana?
Well,
Yeah.
L1
Yeah.
is going to be the line x equals y.
Okay, great. How did you figure that out?
Because e to the 0 is 1, so when h is 1, it's, so then you get x equals y, because that's how you get e
Right.
to the 0 when it's e to the x minus y.
And exactly. So you see that x minus y is 0.
Yeah.
Right. You say, well, look, L1, that's L1 is the guys for which e to the xy is 1, namely e to the 0. You take log of both sides, and you see that that tells you that x minus y must be 0. Okay, in other words, x is y. Okay, great. Okay, so that's L1. Can anyone give me some other line? Some other convenient line? Say, L. Well, in general, of course, right? L. Yeah, Peter.
L of E.
Great. L of E. Great. L of E, right, is going to be the guys such that e to the x minus y is e to the 1. Right? In other words, x minus y is 1. Right? So y is x minus 1. Y is x minus 1. So y is x minus 1. So another one, y is x minus 1. That's LE. Okay? Right? And so on and so forth, right? What's the, if I look at x minus 2, what's that? Going in from the opposite way, what's x minus 2? Y equals x minus 2 will be LE squared, right? This one will be LE squared. Oops. LE squared, LE cubed, LE to the 4th, blah, blah, blah. And so you see that if you looked at this thing from the side, it's, if we look at this thing from this angle, what we see is the exponential function, right? We see the exponential function goes 1, e squared, e cubed, e to the 4th, etc. Right? And what happens as we go this way? Well,
Becomes closer to 0.
yeah, becomes closer to 0, right?
1
So
over the inverse of E.
1 over e. Right? So here we have 1 over e. Here we'd have 1 over e squared. Right? In other words, e to the negative 1, e to the negative 2, etc., etc. Right? And so the pattern continues. It's still the exponential function, right? Just you cross the axis. Okay. Right. So the picture. This allows you to draw a picture. And you say, well, look, my picture is going to look something like this, right? This is x y, right? Then, and it's sort of hard to draw, but maybe it's impossible to draw. I'm going to draw like this. Let me leave this thing. So, basically you'll see some sort of it'll maybe I should this picture should be turned around, but I can't, for some reason I can't do it that way. But anyway, it's like this, right? You have this. I've actually flipped this thing over, but anyway, the picture will look something like this, where if you look at this thing from the side, right, you're going to see the exponential function, right? Like e squared, e cubed, blah blah blah, e to the negative 1, e to the negative 2, etc., etc.
So wouldn't this just kind of be like a form of like a curved plane?
That's right. That's right. So it's
Infinite,
the picture of the thing is just it's a plane. It's a sheet of paper. It's a sheet of paper that, seen from the side, is the exponential function. Right. Okay, last one. F of xy is sine of x squared plus y squared. Okay, so what's the answer? Alana?
Well, we know that sine of 1 is 1, so L1 is the circle.
Wait a second. Sine of 1 is 1?
Isn't it sine of, oh, no, it's not.
Sine of pi over 2.
Yeah. So then isn't it going to be a circle again now?
So, right, so if we look at, say, pi over 2, then that will be the circle of radius 1, certainly. I'm sorry. Sorry, what am I saying? If we look at the circle of radius pi over 2 square rooted, then that certainly gets mapped to 1. But is that everything that gets mapped to 1? No, far from it. Right? What gets mapped to 1? 3 pi over 2.
On a square root there.
Okay.
Circle.
So, right, so you think, well, sine of x squared plus y squared right? For that to be equal to 1, well, what do we know? What does that tell us? Right? You're looking at L1, say. Yeah. What does it tell us? That tells us that x squared plus y squared equals
5 over 2 or 3, or like pi over 2 times k.
pi over 2.
Plus.
Yeah. So it could be pi over 2. It could be 3 pi over 2.
Yeah, plus pi.
It could
Add
be,
pi, yeah.
right? And then adding on
3 over pi over 2.
copies of
Pi k.
yeah, copies of 2 pi basically, right? Where k is some integer, right? Right. So and in general, how does this work? You'd say, well, look, sine of x squared plus y squared, for that to be equal to some height, well, what's the answer going to be? What points get sent to that height? Anyone know the answer? No? Hey, yeah, Flo.
Where x squared plus y squared equals sine inverse of h.
Okay. X squared plus y squared equals sine inverse of h. That will give you one of the circles, but then you have to throw in all the other guys.
It's like plus pi k.
So it'll be, well, it'll actually be plus
Plus or minus?
k times 2 pi, but then you also have to throw in the other sort of like, I'll show you. Right. If this is your height h, right, then this thing here will be sine inverse h. But you have to throw, so putting in multiples of 2 pi gives you everybody on the left bump, but you also have to get these guys. So let's throw them in by saying that this is pi minus this plus copies of 2 pi, right? So it'll be pi minus sine inverse h plus copies of 2 pi. So it could be either any one of these things. So in any case, you get circles where the radii are the square roots of these numbers. So this one is more complicated.